Ever wondered what's really going on inside your kettle when you're making coffee? Today, we're diving into a force so powerful it pretty much dictates your morning routine and so fundamental it makes all life on Earth possible. Yep, we're talking about hydrogen bonds.
We've all been there, right? You're hungry, you're staring at a pot of water, just waiting for it to boil, thinking, come on, what is taking so long? It seems so simple, just heat and water. But it turns out we're fighting a totally invisible battle every single time we make pasta.
You see that long wait? It isn't just about how hot your stove gets. No, it's about a powerful hidden force at work inside that pot, a force that stubbornly holds every single water molecule to its neighbor.
See, you have to remember that molecules aren't just lone wolves floating around. They're constantly interacting, pulling on each other, clinging to each other. And when it comes to water, that attraction is just phenomenally strong.
So, let's put a name to this microscopic culprit behind our slow-boiling pasta water. It's called the hydrogen bond, and you can basically think of it as an invisible superglue holding all the water molecules together.
So what is it exactly? Well, a hydrogen bond is a special kind of attraction. It's very, very specific. It only happens when a hydrogen atom is already locked into a molecule with one of three very specific elements: nitrogen, oxygen, or fluorine.
Honestly, think of it like a simple recipe. You start with a hydrogen atom. You stick it to an oxygen, nitrogen, or fluorine. Then you just bring another one of those molecules close by, and bam! An instant, powerful attraction just snaps into place between them. That's your hydrogen bond.
Now, to really get why this attraction is so strong, we need to zoom in and look at the structure of a single water molecule, H2O, because it turns out not all parts of the molecule are created equal.
Inside that water molecule, the oxygen atom is kind of an electron hog. It pulls the electrons it's sharing closer to itself, which gives it a slight negative charge. And that leaves the two hydrogen atoms on the other side with a slight positive charge. The result? The water molecule is polar. It has two poles, kind of like a teeny tiny magnet.
Okay, this is a really crucial point. The covalent bonds holding the hydrogen and oxygen atoms together inside a single water molecule are incredibly strong. But the hydrogen bond, the one that attracts one water molecule to its neighbor, it's actually much weaker in comparison. It's more like a strong handshake than a permanent weld.
So what happens when you get billions of these tiny little magnets together in a glass of water? Well, they don't just float around randomly. Oh no, they get organized.
I love this analogy from the source material because it's just perfect. In a pot of water, it's literally as if all the individual molecules are holding hands with their neighbors, creating this huge interconnected network.
And it all comes down to that simple dance. Opposites attract. The slightly positive hydrogen end of one molecule feels a magnetic pull towards the slightly negative oxygen end of the molecule next door. This attraction, repeated billions and billions of times, is what gives water its famous stickiness.
Now this all sounds pretty good in theory, right? This whole hand-holding idea. But how do we know it's really that big of a deal? Well, the proof is in the data. And trust me, it is dramatic.
First, let's just get a basic rule of chemistry straight. Generally speaking, the heavier a molecule is, the more energy it takes to get it moving fast enough to boil and turn into a gas. So heavier means a hotter boiling point. Pretty simple, right?
Okay, let's look at the data. Just focus on that top row of numbers for a second, for group 4. As you go from methane on the left to the much heavier tin hydride on the right, look what happens to the boiling point. It goes up steadily, -161, -112, -88, you get the idea. It's exactly what we'd expect. The heavier the molecule, the hotter it needs to be to boil. The rule works perfectly here.
But now, look at the other rows on that chart. Let's just take water, H2O. Based on its weight, its boiling point should be way down around -80 degrees Celsius, but instead, it's 100 degrees. And look, it's the same wild story with ammonia and hydrogen fluoride. These three molecules don't just bend the rule, they completely shatter it.
So what on earth do these three rule breakers have in common? Well, they're the ones with hydrogen bonded to nitrogen, oxygen, or fluorine. They are the only molecules on this chart that can form those powerful hydrogen bonds. All that molecular hand-holding requires a massive amount of extra energy to break them apart and let them escape as a gas.
And this brings us right back to your kettle. The heat coming from your stove isn't just making the water molecules jiggle around faster. No, a huge portion of that energy is being spent just to break those billions and billions of tiny hydrogen bond handholds between all the water molecules.
So that number we all know, 100 degrees Celsius,
it's not some random number. It is the precise temperature where water molecules finally gain enough energy to overcome that sticky network of hydrogen bonds and escape into the air as steam. That's the moment your water finally actually boils.
And think about this. Without this bond, water would just be a gas at room temperature. Life as we know it, it just couldn't exist. This one tiny attractive force, all because of a lopsided molecule, literally shapes our entire world. It really makes you wonder, what other secrets does it hold?